Good evening, everyone. So if you're watching this, that means that some technical hurdle has impeded me from being there with you, so you get this pre-recorded version. I would have loved the live version, but feel free to contact me if you have any lingering questions after this. I wanted to introduce myself. I'm Mario Negrello, PhD. I am assistant professor at the Erasmus Medical Center, where I teach computational neuroscience, which makes sense given that I have been asked to introduce you the movie In Silico here. And I would like to share a couple of thoughts with you from the perspective of a working computational neuroscientist. When I read the synopsis of this documentary, I knew I had to watch it. But when David invited me to introduce the movie to you, I made the conscious decision not to watch the documentary before preparing this. I wanted to give you my unbiased opinion of the endeavor of simulating a human brain and what does it mean in the context of modern science. You're going to see a movie about Henry Markram and the Human Brain Project, and I know those from the inside. I hope to give you a balanced perspective as a primer before you go into watching In Silico, and I will watch it with you and I will see how consistent my take has been. As I mentioned, I'm a practicing computational neuroscientist with experience across neuroscience and AI. I have worked with evolutionary robotics, reinforcement learning, and computational neuroscience, which means to simulate both the brain as a physical entity using the rules of physics applied to biological organs, and of trying to understand what it gives rise to intelligence. The question that occupied Henry Markram is the same one that the documentary asks, and one that I have often asked myself. Is it possible to simulate human brains? So this proposal started with the European Union saying, I'll give you $1 billion for you to advance your science. Those were the flagships. These were humongous grants, scientific grants, with each involving very many labs across Europe. So the point was integration here. And there were two awardees. One of which was graphene and the other one was the Human Brain Project. They already split this $1 billion and then they split further across the many labs that participate. Now it takes a very special type of person to push such a proposal involving these many labs. In fact, it takes someone that is driven and to a certain extent megalomaniac. But when I saw the initial discussions regarding this application, I saw that Henry Markram was a man with a plan that was both political but also realistic with respect to the goals of science. The Human Brain Project now is a reality and started in 2013. As you can see here, it involves a vast set of goals involving exploring the brain simulations, silicon brains, understanding cognition, medicine, and robotics, as well as massive computing, looking into the social, ethical, and reflective aspects as well. I believe that the process of making brains is not very much different than the process of making sausages. The truth is that you can't make brains without breaking a few eggs. And we commonly say in Portuguese, if you know how to make sausages, you might not want to eat them. You can see here a sausage. You fold the sausage and you neatly apply it on a cake bun. And the process of making sausages is not pretty, but the thing is pretty darn delicious when it's done. What does it mean to make a sausage? For working scientists, making a sausage means we have to fight for funding. We have to convince people that the research we're doing is relevant, even though people might not understand the fundamental aspects of that research. We may then have to sell and maybe in certain cases oversell the research. Scientists are subject to the rule of publish or perish in a very competitive environment, which introduces a cost into what we're doing. The neuroscience community is formed by scientists that cover a very vast and complementary spectrum of expertises. It's a community with very many perspectives. And we start with neurobiology, which studies what brains are made of, the neurons themselves. going through cognitive psychology, which attempts to understand what brains can do, and reproducing or emulating various aspects of brains and intelligence, as what computational neuroscience and neurocomputation does. Neurocomputation is more related to artificial intelligence, whereas computational neuroscience is more concerned with reproducing the biophysical aspects of the brain, that is, emulating neurons in detail. What the Human Brain Project is whatever these working scientists believe is the best way to move our understanding forward. So you have these massive and distinct ways of approaching the question, each of which has to contribute its understanding to the others. Making a brain is not simply cobbling up a bunch of neurons together and hoping for intelligence to emerge, but really inspecting all of the elements in conjunction, which is not obvious how to do because you have a lot of agreements to make. But if you're writing a proposal such as the Human Brain Project, you have to try to give a consistent view of what the grand objective will be. And here I get into the aspect of the trade-off that exists between claims and objectives. If you want to convince someone to give you $1 billion or $500 million or $5 billion, there are some trade-offs that one is committed to. On the one hand, to sell something that is that expensive, it is common practice to claim feasibility. You say, well, yes, I mean, this can be done, and we should do it, and we also have to say that it has to be done now. On the other hand, there are actual factual objectives that those writing the grants have in mind, which are often tangentially related to what the claims are themselves. The claims may say things like, we will simulate a human brain and the brain will be intelligent and we will cure disease. And while that is true as a claim, as a grand objective, most scientists I know are very aware that the claims are ideals that we approach by paving the way towards and producing intermediate results that, at least in principle, address the actual claims. So making a brain is this confluence of multiple viewpoints of what a brain is made of, and making sausages is equally messy. Making brains is messy. We have these multiple viewpoints that are essential components, and individual scientists work within their expertise to reach those goals. If we were talking live, I would have given you the question in a poll of whether it is possible to understand the brain. In this poll, I would have given you a very bipolar option. I would have asked you yes or no. And my expectation is that even though in this dichotomy you're forced to choose one particular solution, in fact, in a slide subsequent, I would have asked you, how about I change the question a bit? Is it possible to understand the brain? And there are two answers, yes, but, and no, but. What do I mean by this? Is that we have more context when we're saying what explaining the brain means. There's a philosophical aspect to it, whether what does it mean to understand the brain. And some other people might say no, but they might say no, but there's lots of things you can in fact do which are objective and solid results. You can continue to study the neurons in detail. You can do a lot of electrophysiology and experiments that will bring us closer to the components of this massively complex system. And the question that naturally poses itself is, is the time right for such a proposal? We have amassed a mind-boggling amount of data, with loads of data about the connectome of the brain. So these tracts that you see here on the very colored lines, the diffusion tensor imaging retrieves them, and they give us a very good idea of how the brain is connected, at least at a mesoscopic scale. We might not yet understand how they all interact, but we have sufficient theories that bring different aspects of the puzzle into account. We also have incredible data. So here we have two-photon imaging from the cerebellum, which is a part of the brain concerned with motor movement, that where you can see the individual activity of multiple Purkinje cells. And in fact, you see these lines, these slits that go on the side. These slits are the actual dendritic trees, the neurons themselves. They are actually that flat. You're looking at them from above, and so you see them as lines. You also see some dots shining there. This two-photon imaging technique gives us a real-time understanding of the activity of the brain. And Human Brain Project was not the first attempt to simulate a whole brain. In fact, Eugene Izhikevich and Gerald Edelman, some years back, maybe a little bit over a decade back, managed to simulate a cortical thalamic loop with all of the neurons that we presume we have in a human brain, based on data from diffusion tensor imaging. So it is feasible. Now, how much do we understand from that? That's a question we can pose, but I can tell you, for instance, that many aspects, for example, in terms of resonance and in terms of frequencies that the brain produces in its waves, can be reproduced at this level without having been priorly tuned to reproduce them. So there is already understanding and data that we obtain from this. In fact, I have looked into activity of vast areas of the brain, and often they resemble the types of dynamics that we observe here. Now, what does it mean in terms of behavior? That's an important question that we have to answer, but we have to answer on the basis of certain elements that we can combine together. The Human Brain Project stems from the Blue Brain Project, where they actually have reconstructed a cortical column of a mouse you see the activity here of individual neurons. And this activity has been tuned exquisitely according to the types of dynamics and morphologies that multiple neurons have. The point that I'm making here is that we have tools that allow us to begin the process. It is a step along the ladder, and then we can understand and try to relate this data with what we see in reality to find contrasts or indeed agreement between the two, to see what difference actually in the data makes a difference in the brain. Above and beyond the predictions, we are doing science, we're making sausages, and so potentially some of the most relevant outcomes of the human brain have not been exclusively in what brains are that we're simulating, but in the data that we're acquiring and in the framework and tools that we're developing, which are being made open. And so this, I think, is one of the core outcomes of the human brain. We get more able to simulate better brains in the future because we're creating open neuron databases, channel databases via, for example, the Channelpedia or eBrains as a platform for simulation of brains. We're cross-linking labs across Europe that are working from different perspectives, attempting to integrate their own observations and results. We have open simulation tools, and we advance standards for making better science so that we make it reproducible. The bottom line that I wanted to share with you here is that this is a human endeavor, and it's fraught with human qualities. So are we ready? And I would like to answer for you. So, are we ever ready for this? We're never truly ready, and yet this is always the right time. Is it worth it? Oh, hell yeah. I mean, the amount of knowledge that we're amassing clarifies certain aspects and allows us to exchange more and more fundamental insight about brain dynamics and function, also including even disease such as epilepsy, or models of epilepsy that are very powerful, and they have been introduced in the clinic. Will it succeed in the end? We have to define succeed properly. I think that it succeeds as human science. I mean, it puts together this enormous amount of labs to work across Europe, bringing new experimental data together, putting minds to work with each other and advancing our joint objective. If you want to know more about computing brains in general, I would like to pitch the minor that I organize shamelessly at the context of the Erasmus Medical Center. It is a minor for bachelors. And there we discuss the relationships between biology and computational neuroscience, as well as artificial intelligence, to try to make an integrated perspective on this. I would also like to pitch the podcast from the Brain Inspired podcast, where very detailed discussions with the foremost neuroscientists of the age are giving their perspective on whether on the feasibility of these questions. I sense you will notice quite a bit of optimism across a number of different scientists, and I wanted to share with you these resources. I have nothing else to say today, so the next thing I wanted to tell you is enjoy the movie, enjoy In Silico, and I hope that my perspective here gives you a little bit of latitude to interpret the movie and the contents of the movie within the overarching context of science. Maybe this is going to be the same message as the documentary directors wanted to convey in the end. It is a human endeavor, and we basically are making sausages most of the time.